We're going to be talking about what are called condensation and conjugate addition reactions of carbonyl compounds. When I was putting this one together, I always search the internet looking for some things to put on to try and help the concepts. Found the link to this is here. This is a very simple little slide share presentation, but actually what it does do is really emphasizes the point that most of the reactions you learn in organic chemistry in probably your first 3 courses, most of them are reactions between acids and bases and nucleophiles and electrophiles. And quite often the acid-base reaction is one of the first reactions to kind of determine what will be nucleophiles and what will be electrophiles. And this chapter really emphasizes the fact that one of the things we want to do when we're looking at these reactions is identify what is our nucleophile and what is our electrophile, and then be able to figure out what happens. And we know that nucleophiles, we talk about them attacking electrophiles, and that's what this is. This is a bromide nucleophile attacking an unsuspecting carbocation. But that's what most of the reactions we've done in this class are. We've had the odd radical reaction, and then redox are a little bit different because they're electron transfers, but quite often those most of the other reactions are nucleophiles reacting with electrophiles. So part of what we're going to be doing in this chapter is taking a look at, we've seen some carbonyl chemistry, okay, so and last chapter we talked about this keto-enol equilibrium, and we talked about the fact that quite often ketones are decent electrophiles, and this enol is a nucleophile. So even ketones have this dual character. They can isomerize to these enols. This is going to be an electrophile. This is going to be a nucleophile. And we were looking at some chemistry last chapter where we were making our carbonyl compounds, the nucleophiles, by removing an acidic proton. So we typically removed an acidic proton, but let's go back to chapter, I believe it was 16 and 17, or yeah, 16 and 17, where we talked about the carbonyl group as an electrophile. And we're used to these nucleophiles attacking the carbonyl carbon, and then forming this tetrahedral intermediate that can then go on to do different things. We did that in chapters 16 and 17. Last chapter we saw that we could make carbonyl compounds nucleophiles by removing a proton and making these enolate anions. That negative charge is shared between the oxygen and the carbon. Most of the chemistry we saw occurred from the carbon. It can also occur from the oxygen. We didn't get into that. But this thing is now a nucleophile, and it reacts with electrophiles in a nucleophile-electrophile type of reaction. And in this case, our nucleophile abstracted the bromine, and we get a bromination reaction. Well, will an enolate attack a carbonyl compound? We can make a nucleophile, and they're also good electrophiles. So can we make this nucleophile react with this as an electrophile? And the answer is yes, we can. We can push our arrows, and our pair of electrons, there's a pair of electrons there, will reorganize and attack the electrophile, and we get formation of a bond between this carbon and this carbon, and that's what we see there. So what you're going to see here is I'm going to be making my nucleophiles red and my electrophiles blue, and I tried, I may have missed once in a while, but the new bond that formed will remain black. So our nucleophile attacks our electrophile and forms a new bond. And we get this thing. We're used to seeing this thing. What can this thing do? This is just the tetrahedral intermediate that forms, and it's going to depend what else is there. There's no good leaving group here, so this thing is probably going to now act like a base and go and seek out a proton somewhere, and that's exactly what we see. Our final product is this thing. So here we see we can take acetaldehyde, react it with base. We don't need a full equivalent of base, just a catalytic amount of base, and that pulls off the proton on one of the acetaldehyde molecules, that becomes nucleophilic. There's enough acetaldehyde around that it can seek out and react with one acting as an electrophile and form this tetrahedral intermediate. That thing is now basic enough to pull off a proton from one of the starting materials to start the cycle over again. And this is our product. This 3-hydroxybutanol is our product. So we react an aldehyde. The product is both an aldehyde and an alcohol. We call this the Aldol Addition. So we're going to talk about this a little bit today. Let's take a closer look. So we've already discussed this. The first step in the reaction, we have some base around, and it removes one of the hydrogens on the alpha carbon. In this case, we have an aldehyde, so we only have one alpha carbon. It removes that proton, and we end up with this enolate anion. And we know that that charge can be shared. That's the first step. The second step then just involves the nucleophilic attack. I got these from the textbook, so the colors are off, but the rest of the presentation, I got the colors correct. So this is our nucleophile, and it just attacks our electrophile, and it forms a bond between this carbon, and we get this alkoxide-like anion. And it's got that negative charge there. We know that alkoxides are decent bases, and now instead of hydroxide acting as the base, that alkoxide can pull off a proton. It can pull it off from water, or it could pull it off from another molecule of acetaldehyde, right? So there's lots of things that have protons available.
What would stop the base from taking the hydrogen off of the carbon atom that's attached to that was like newly formed with the carbon atom on the left?
So what would stop the...
There's a hydrogen atom on the carbon on the left there. What on the left one? On the left. No, sorry. There's 4 carbons there.
This carbon atom?
One to the left. Yeah, that one. What would stop the base from taking the hydrogen off of that?
Well, okay. It could, but there's a lot more water around. There's a lot more water. There's not very many of this, right? As we go further and further into the reaction, the concentration of this compound gets more and more. You may take that proton off, but at the start of the reaction, there's none of this around. As the reaction proceeds, there's lots of water, right, for it to pull the proton off. So you set the conditions up. These side reactions often do happen, and you try and set the conditions up so that that they're less favored. And in this case, it's going to be less favored because you're doing this reaction in water. So, and that proton is somewhat acidic, but we'll see there's another reaction that'll actually is even more favorable, which we're going to see in just a second. So with ketones, the addition step is unfavorable due to steric factors, and equilibrium favors the reactants rather than the products. We saw this reaction went in decent yield with acetaldehyde. With ketones, the reaction is less favorable because this step is disfavored, because as soon as we put a ketone, another carbon there, this is a poorer electrophile. It's not as good of an electrophile. So with ketones, this reaction is not quite as good. We can force it to go, and there's lots of useful reactions that do an aldol, but we set the conditions up to make it happen. In the most case, it's unfavorable. Reactions of both aldehydes and ketones can go to completion by using a strong base in an aprotic solvent. That's a slightly different type of reaction. We'd need a full equivalent of base. The product we can see in a second can also undergo a dehydration reaction to yield an alpha-beta unsaturated carbonyl, which we're going to see in just a second. Right now, in fact. So these things, this reaction is very favorable for a proton to get pulled off, and then we form this thing, which is an enol, and you can get rearranged. I'm sorry. Pull a proton off, form the anion, and then knock off OH minus. We end up getting, you can see that this is catalytic. OH forms the H2O, but then the OH gets kicked off. And this could also be E2. It's showing it as an E1CB I don't know if you guys went through all the mechanisms, but this could also be an E2 type of elimination. But you get this, we talk about it, there's the alpha carbon, there's the beta carbon. So we call this an alpha-beta unsaturated. This is an enal. If it was a ketone, it would be an enone. But we have unsaturation between the alpha and beta carbons. So dehydration of this happens a lot. And in fact, in some conditions, it's hard to stop it at the aldol. Most of the time, we end up with what we call the aldol condensation product. So the addition product, this is the addition product, and then the addition product undergoes a condensation reaction to form that. So we talk about aldol additions and aldol condensations. The retroaldol reaction can occur as well because all of the steps are reversible under conditions where we have a catalytic amount of base, we're in a product solvent. All of those reactions are reversible. We can actually start with beta hydroxy ketone or aldehyde, and in this case it's a beta hydroxy ketone. This direction is actually favored. Okay? If this were the aldehydes, it typically will favor this a little bit more, but when we have ketones, because of that electrophilic addition step in the forward reaction, the retroaldol reaction is quite easily to make happen if the products are ketones. So you'll see at the bottom I say provide a mechanism for the reaction. It's just the reverse of the reaction that we just did. Give that a try. These reactions can also go under acid catalyzed conditions. Under acid catalyzed conditions, it's slightly different. What happens now is our ketone acts as a base. We need a very strong acid, and it's not a particularly good base. This equilibrium greatly favors this side, but what happens is once we form this thing, it becomes a very good electrophile. And don't forget that we're in equilibrium with the enol. So we have our ketone, we protonate it, we have a good electrophile. Sometimes it's going to make the enol. Sometimes it's going to exist. If we have lots of enol around, we have a good electrophile and a decent nucleophile. So what we need to do is have a collision between an enol and a protonated ketone, and then we can get the addition. This will act as the nucleophile, and it will attack the electrophilic carbon, the souped up electrophilic carbon because we protonated it, and we get the same bond formation. And then finally, this thing just deprotonates, and we end up with, we can end up with our condensation product. Under acid catalyzed conditions, it goes mostly to the condensation product, our alpha beta unsaturated, in this case an enone. So here's just showing you that it can be useful for synthesis. We could imagine taking our aldehyde, doing an aldol reaction. Once we have our aldol product, we can do different things with it. We could reduce the ketone and get a diol. We can do the dehydration, get the alpha-beta unsaturated compound. There's different ways we can completely reduce everything to end up getting a saturated alcohol. We can actually just reduce the ketone group with lithium aluminum hydride, or we could just reduce the carbon-carbon double bond and get an aldehyde. So these are synthetically useful and lead to a number of different intermediates that are often involved in organic synthesis. So now you could imagine we could do reactions. What if we have two different aldehydes and we throw up a mixture and we throw this in base? So you can imagine now what can happen is one of these can be a nucleophile, one of these can be an electrophile. So if I remove that proton, that'll become nucleophilic, and it can react with that. It can also react with itself, so we can end up getting 4 different products. So this is showing 3-hydroxybutanol is from 2 molecules of ethanol. This undergoes an aldol. This undergoes a self-aldol, and we can have a cross aldol products where this is the nucleophile and this is the electrophile in the case of here. And we could also get a case where this is the nucleophile and this is the electrophile. We get 4 different products. Okay, should be able to figure out those 4 different products. Take a look, see if you can figure it out. Now, the first thing you should be saying when you're thinking chemistry now, that's not very useful, right? We don't want reactions that give us 4 different products and make us have to separate them somehow. That's really a pain. So what we want to do is be able to set things up so that we don't get 4 different products. We want to make it useful. We can do that by we can make useful cross-aldol condensation reactions by setting up our conditions in a particular way. So if we take these 2 aldehydes, we see this one has no hydrogens on an alpha carbon. So that can only be the electrophile. Because it has no hydrogens in the alpha position, we can't pull a acidic proton off and make it nucleophilic. So this one is always going to be the electrophile there, blue. This one, we can pull a proton off and make this thing nucleophilic. And then we can get our crossed aldol product. There's only one product that we can get. Now, we want to avoid the self-reaction of this thing. How would we do that? We're the chemist, and we're in control. We have to think a little bit about how we would set things up in the lab. So what we might do is, you could imagine, we can take this. It has no alpha hydrogens, put it in solution with our base, okay? And the hydroxide, if hydroxide is our base, it can attack that carbonyl, but it has no place to go, and it's just going to set up an equilibrium where the hydroxide attacks the carbonyl, forms a tetrahedral intermediate, and then goes back. Most of the time, this is just going to exist as the aldehyde. Every once in a while, it's going to get attacked by the hydroxide acting as a nucleophile, but it's not going to stay there. It has no place to go. As soon as we have that set up, we slowly add this thing. There's base around. If we add it slowly enough, it's going to pull off a proton, form our nucleophile, and the only electrophile around is this one, because this is in very low concentration. We're adding it slowly. As we add it, it gets changed to the enolate. The enolate attacks the electrophile, and we avoid the self-reaction with the acetaldehyde, and we only get one product. You can see we did the same thing here. No alpha protons, and here we do have alpha protons. So our crossed aldols, we set the reaction up so that we can get the product we want. In this particular instance, you'll see that there are no protons on the alpha carbon now, so this will stop at the Aldol Addition product. We cannot make the unsaturated compound because this carbon has no hydrogens to be removed to make the unsaturated compound. Another way we can set up crossed aldol condensations that's useful, similar, but we don't have to worry about the self-reaction. If our nucleophile is a ketone, this is so much more electrophilic than the carbonyl carbon of the ketone. We don't even have to worry about the slow addition. We can just throw these together, add some base, and we can end up getting our aldol condensation product. And that is because we form this thing as the nucleophile. It reacts very quickly with this carbonyl carbon, and it reacts much slower with this carbonyl carbon. So we don't have to go through the process of the slow addition anymore. As long as we have a ketone as our intended nucleophile, then we don't have to go through the special conditions. If our intended nucleophile, remember with a crossed aldol condensation, we have one ketone or aldehyde, an aldehyde usually, that we want to be our electrophile, and the other one we want to be our nucleophile. So we have an intended electrophile and an intended nucleophile. And if our intended nucleophile comes from a ketone, it's easier to control the reaction because of the poor electrophilicity of that carbonyl carbon. And we can get these crossed aldol condensation products. So you might want to provide a synthetic pathway for this. I don't think you guys have done this lab yet, but you'll be making this in the lab. So you'll want to know the mechanism for that reaction. Have you done this lab? Oh, okay. So you guys know all about this chemistry. Another way to make crossed aldol products, slightly different. Now we can no longer use catalytic amounts of base. We have to use a full amount of base. But what we can do is preform our enolate by reacting it with a very strong base and under dry conditions. So if we take a ketone, we react that with lithium diisopropyl amide, very strong base. We're at very cold temperatures. We can form this enolate, and we can actually get, this reaction goes pretty well to completion because this is such a strong base. So we mix these two up. We actually put the LDA in solution and we slowly add our ketone, or we can do it the other way around. But we preform our enolate, and then we slowly add the aldehyde, still at -78. Why do we leave that at -78? Can anybody think why? Notice now that I pulled this proton off. How come I didn't pull this proton off and make the other enolate? Kinetic control, exactly. So this controls the reaction kinetically. It gives us some control. We can make the kinetic enolate. If we let it warm up, the kinetic enolate is going to equilibrate with the thermodynamic enolate. But this way, we get very good regio control. We only have a predominance of the one enolate. There's not an equilibrium between it and where the double bond is there. And we get our aldol product. Then we just have to quench the reaction at the end. And we end up getting our Aldol Addition products. This is also nice because we can stop at the Aldol Addition product and not necessarily get the condensation product, which is sometimes difficult to do under the other conditions. The other conditions, you often get the condensation product. What if our intended nucleophile and our intended electrophile are on the same molecule? Well, as it turns out, 4, 5, 6, and 7 ketoaldehydes, so these are beta dicarbonyl, I'm sorry, not beta, they're dicarbonyl compounds. They have 2 carbonyl compounds. And we look at this thing and we take a look and we see, okay, there's a good electrophile. Can we make this thing nucleophilic? And we can. If we pull off this proton, it sets up to form a 6-membered ring. And we get an internal cyclization reaction, usually difficult to stop, and we ended up with the cyclized alpha-beta unsaturated enone in this instance. This is also, notice this one now, notice this is slightly longer, and we form a 5-membered ring. So we form that 5-membered ring by pulling this proton off, and it attacks here, and that gives us a 1, 2, 3, 4, 5-membered ring. Okay? So let's take a look at the mechanism for this reaction. One of the things we want to realize, first thing a lot of people are wondering is, how do we control this? Because can't we pull any one of these protons off? And the answer is yes, we can. But any one of those protons going to lead to a successful reaction? Only one is going to lead to a successful reaction. So if we throw it up this way, we can see that we can remove this proton. If we remove that proton, we form this enolate. There's a negative charge there. Because of the proximity effect, 5- and 6-membered rings are easy to form. When we make this enolate, it's floating around. The molecule is twisting and turning and getting different conformations. And as soon as it gets in this conformation, this is very close to, we have a nucleophile very close to an electrophile. The bond forms, the ring closes, and then it pulls off a proton and forms our Aldol Addition product, which goes on to form the alpha-beta unsaturated compound. If we pull off this proton, or one of these protons, if we pull off this proton, we form the enolate, but it's hard for a conformation to find itself and form that 7-membered ring. 7-membered rings, if you ever made the models, are a little bit more difficult to make than 5- and 6-membered rings. Okay? If we pull off this proton, the problem is that we have a sterically hindered, we have a poorer electrophile. So in this reaction, let's go back. We form, all of the enolates can form. We can pull off this proton, a proton from this carbon, a proton from this carbon, and a proton from this carbon. But if we pull off a proton from this carbon, we can form a 6-membered ring. If we pull off a proton from this carbon, we can only form a 4-membered ring. And we know that 4-membered rings are highly strained and difficult to make. So in fact, the reverse reaction would probably go. If we pull off this proton, same thing. Now over here, if we pull off this proton, we could form a 5-membered ring, but it's a much poorer electrophile. So what happens is, even though we pull that off, the reaction is so slow that eventually a proton hops back on before it can react to form the 5-membered ring at that electrophilic carbon. So these ones are nice. Remember, one of the things you want to remember, you may want to write it down, is that aldehydes are better electrophiles than ketones. Okay? And that's what helps these reactions go. So 4, 5, 6, and 7 ketoaldehydes and ketones can do these cyclization reactions because just think about forming a 5 or 6-membered ring. So the other enolates form, but they're unreactive. The one that will form the 5 or 6-membered ring will be the most reactive, and then if it's going to the aldehyde is the very most reactive. Okay, so now is there an ester form of the aldol condensation? So now instead of using aldehydes, we're going to start off with esters, and if we pull a proton off of one ester, can it attack the other one? They're not very good electrophiles. Esters aren't very good electrophiles. So why might this reaction happen? It's not going to happen very often, we might think, but look at this. It goes in high yield. So this goes. It's named after this guy, Rainier Ludwig Claisen. It's called the Claisen Condensation, discovered in 1887. One of the things that helps us out is this is not entirely an equilibrium reaction, even though we've shown an equilibrium. So I want you to go back and recall nucleophilic acyl substitution reactions, where we had an ester reacting with a nucleophile. Some of you may have figured out that when these reactions occur, what happens is this comes off as the alcohol, and the nucleophile ends up at the nucleophilic carbon, and we just get a substitution reaction. This goes because this last reaction is less reversible. The best nucleophile will end up staying here. Okay, so our better leaving group will leave, and it usually leaves in its protonated form. So in this instance then, we have, I've drawn one of these as a electrophilic ester, the other as our nucleophilic ester. Once we have our nucleophile, let's just remove one of the acidic protons and the ethanol and form our ethanol, and then this nucleophile just gets bonded to the carbonyl carbon, and we end up with our product. So here's the electrophilic portion. Here's the nucleophilic portion. This is just Nu, right? Just Nu. This is our electrophile, and that's the new bond that formed. And we split off ethanol in this instance. So let's take a look at the mechanism. I see someone writing, so I'll just pause. Go ahead. Okay, so yes, this can pull off. These aren't as acidic as they are in aldehydes and ketones, but they are acidic, and we form this thing. This thing slightly stabilized, so it's not a particularly stable enolate. It's not as stable as the other enolates. But remember, when they're not stable, they also like to react. So most of this is going to go back and forth, but it's fairly reactive, and it's going to attack an electrophilic carbon, even if it's not a very good electrophilic carbon. We form this. This is our tetrahedral intermediate, and then it just knocks off a thiouxide, and this equilibrium lies over here. What else helps us out here? Okay, so this is pretty good, but now we have a proton right here. We don't see it, but it's there, and it's in between two carbonyl groups. When we have a proton that's in between two carbonyl groups, what's going on? Oh, I'm going the wrong way. When we have a proton that's in between two carbonyl groups, it's particularly acidic, and this reaction actually goes pretty well to completion. This is the reaction that drives this reaction to completion is this very favorable equilibrium to leave this anion. The pKa of here, the pKa of this proton is much more than the pKa of this proton. So this is a very, very weak acid. This is a stronger acid. This equilibrium lies here. So our reaction will go and sit there until we quench it. The last step of the reaction, we have to quench. We have to do an acid quench. So we just add some strong acid to protonate our compound and end up with our product. This equilibrium has not really come into play. That's a product that we end up isolating. And it's step 4 that drives the reaction, and then step 5, we have to add an extra acid, a strong acid, to do that, what we call that quench. Just like we had intramolecular aldols, we can have intramolecular Claisen condensation. So as long as we can achieve a conformation, we pull that proton off, and then we get a fairly rapid closure of the ring that drives this reaction to completion. The intramolecular version of a Claisen is called the Dykman condensation, and it's useful for making 5- and 6-membered rings, just like the other reaction was. As you might guess, we can also do crossed Claisen condensations, and we do the same thing. One of our esters has no alpha hydrogens, no hydrogens on the alpha carbon, so it has no alpha hydrogens. So we can't pull them off, and we can't make an enolate of this. We can't make this thing nucleophilic. It can only be our electrophile. This one, we can go ahead and pull off a proton, and we get our crossed aldol condensation. In this particular instance, one of the interfering compounds is going to be the self-aldol, but we do still get significant yields here. Bottom one is the same. We have one which has, this one doesn't even have an alpha carbon, so only this one can be our nucleophile, and it can attack that, and we can end up getting the crossed Claisen condensation. We can also do preform an enolate by using a strong base. Typically we'll do this when we have ketones, and then we can add our ester, and the only possible product is the acylation product. I think that's it for today. Yeah, the next thing we're going to talk about is addition to alpha-beta unsaturated carbonyl compounds. And just like when we had dienes, 1,3-dienes, this is like a 1,3-diene, but now we have an oxygen there. So we can have simple addition, or what we call conjugate addition. We can have 1,2 addition, the nucleophile added to the 1 and 2 position, and here it's added to the 1 and 4 position. So it's simple versus conjugate addition. This is often called the Michael addition, the conjugate addition. That's what we'll be talking about next class. I have some yeah, we'll wait, because I don't want to start this topic now. We don't have enough time. I have some quizzes to hand back.